Yes, can you hear me, Christiana?
Okay, that's a yes.
And hello.
Okay, well, I think we can start. So thank you all for coming to the second section in the winter school. I'm very, very excited to have Professor Kevin Zumbrun, who is originally from Indiana University, but this semester he is the Dean's Distinguished Visiting Professor here at the Fields and associated also with the University of Toronto. He's going to tell us today about stability of roll waves and inclined shallow water flow. Kevin, thank you so much for agreeing to talk to me.
Okay, well, thank you for that nice introduction, and thanks very much to the organizers, Leo, Steve, and John, for making this possible, this nice school, especially to Leo for providing a version of my slides with videos that work. So that's, you'll appreciate that. Okay, so maybe I don't want to forget. So this is, I'm going to describe work with Blake Barker, Matt Johnson, Pascal Noble, and Miguel Rodriguez, and Zhao Yang. So these guys, this is, I'm going to describe, it's kind of an advertisement for my course a little bit. A lot of description of different things. I'm not going to give proofs, but this is work, it's all very recent. It's in the last 10 years. And when we started, there were many mysteries. We didn't know if there were any. We like to study stability, but we didn't know if there were any stable roll waves at all. And there was some conflicting evidence on that. So I remember at one point up in the upstairs visitor's office with Blake Barker, Miguel, and Pascal, we were looking at the computer screen waiting for our numerical stability study of one wave, which we picked at random. And the light was green and it was stable. And so we knew things were going to be okay. Okay, so now I'm going to describe a little bit of that. Okay, so first, this was actually, I'm very happy. This is the first model that was ever shown to me in my fluids class by Paul Garabedian, a shallow water flow model. And it got me hooked on shock waves until now. So that's kind of fun. And now it shows up again. So this is shallow water flow in a channel, but we're taking a 1D approximation. And so you just have height here. Where did it go? Okay, H is height, Q is flow rate, and you assume that the flow rate is proportional to the height. And that not proportional, but a function of the height, a varying function. And with that, you have a genuinely nonlinear scalar conservation law, as we just talked about. And these form shocks. And that's sometimes called a hydraulic jump or a hydraulic bore in this context. Okay, well, I've drawn two things. I've drawn a dashed line with an actual discontinuity, and I've drawn a bold smooth line. And that's because sometimes viscosity comes into play. I'm actually today, so I guess that Cole will speak about inviscid and viscous problems. I'm going to talk about relaxation systems. There's somewhere in between the two, so that works nicely. Okay, so where did this come from? I didn't really know for many years, but now we're studying this. It comes from the San Venant equations, which are themselves an asymptotic model in the shallow water limit, and not at all easy to derive, I think. But here they are. Well, now this should look kind of familiar. This is like the Euler equations on the left, except if we leave out the energy equation. So this is isentropic Euler on the left. H is the height, Q is H times U, so height times velocity. So height is basically density. This is an incompressible model, by the way. So height would be proportional to the density per x. Okay, and then Q is still the flux rate. And here we have a pressure function coming in, and P of H is proportional to H squared. And there appears here a dimensionless constant called the Froude number, and it directs the behavior of everything. Here's what it is. It's like a Reynolds number, sort of. It's a typical velocity over a typical height times gravitational constant times cosine of theta. Theta is the angle of inclination of the ramp, and you could just basically think that F gets large as the velocity gets large or the incline gets large. So it's basically measuring the amount of energy in the flow. So things become more energetic with large F and less stable. This is like the left-hand side is exactly compressible isentropic gas dynamics with a gamma log gas, gamma equals 2. That's the, oops, there we go, h squared. Okay, so, but on the right, we don't have 0, but we have some forces here. So this is, so this has been rescaled. So gravity's out of the picture. Gravity is 1. So this is just the gravitational force, and that's accelerating things. And resisting is a turbulent bottom friction. So that is, Q is h times u. So this is really u squared, h minus u squared, where u is the velocity. That's a common model, a Jay-Z model for turbulent friction. Okay, so what is, at equilibrium, the right-hand side should be 0. And that determines Q as a function of h. Q should be h to the 3/2. And that gives formally a Burger's type equation. We have that Q depends non-linearly on h. It's not squared, it's 3/2, but qualitatively very similar. And that's the justification of the previous slide. Okay. Now, when does this make sense? Well, if you're near equilibrium, it should make sense, it seems. But also, there should be some kind of stability condition that makes you stay near equilibrium. And that is what's called hydrodynamic stability. To determine that, you linearize around a steady state. This is defined as stability of a constant solution. So that would be a laminar flow just going steadily down the channel. That would be what you want if you have a canal delivering water, say. That's where you would like to stay. Okay, so it turns out by basically Fourier analysis and just linear algebra, you find that this is equivalent to what's called the subcharacteristic condition. So the model, the isentropic gas dynamics has the full model on the left-hand side has characteristic speeds A plus and minus, which are U plus or minus sound speed, exactly the same as the previous lecture. But then there's this Q prime, that's the Burger's characteristic for this equilibrium scalar model. It must lie in between the other two to have stability, which is like a CFL condition in numeric. It just makes sense. If this, because we have finite propagation speed, if the scalar model is trying to go outside the cone of influence of the full model, that can't work, right? It can't possibly approximate that. Okay, and that's an old condition found by Jeffreys in 25. That's 1925. Amazing that we get to say that now. You make that distinction. So this is very interesting. The scaling of this model is very nice. So it's just Froude number less than 2, period. It has nothing to do with the constant state. Usually it would have something to do with the fluid parameters, but it doesn't. So either all constant states are stable or all are unstable, just depending on as you increase the inclination, say, or the overall speed. So that's really special. Okay, and this is a commonly used model industrially for hydraulic engineering planning, building of canals and so on. Well, what is the Froude number in those contexts? Unfortunately, it's 3 to 10. It's well above this hydrodynamic stability limit. There's a really nice paper. This is a Caltech thesis of Brock in the 70s, and he did amazing experimental work and analytic work, and I really recommend that thesis. I'll come back at the end with a picture of his apparatus, which is fun. Okay, so now I'm going to show you, so what happens, so a nice example is to do what we call a dam break problem. It's really just a Riemann problem. We take constant value to the left, constant value, lower height to the right, and we just numerically solve this. And what we're numerically solving with is Randy Levesque's Klopek, which works great for it. It's not easy at all to solve these nicely numerically. Okay, so anyway, let's see if this still will work. I hope so. Okay, so there we go. Okay, so what happens is, well, it's kind of, this is a Burger's shock or scalar shock. but it has kind of, it's smoothed out, and then it has what's called a subshock. So it is a combination. Viscosity would completely smooth it. And for small amplitude waves, if we made this dam smaller, it would be completely smooth. But if it gets big enough, then it kind of breaks a little. But interestingly, we're pretty far from equilibrium here, and it still looks kind of like the scalar equilibrium system. Yes.
Sorry, so what are the top and bottom here?
Okay, so they're just Q and H. H is the top, Q is the bottom. I really don't need both, but we had both. Yeah, thanks. Good question. You could just look at H because thinking of the scalar model. Okay, so yeah, so it's qualitatively similar. This is F equals 1, so it is in that stable regime where we might expect it to be governed by the equilibrium, but once it stops being smooth, that seems less. Boy, I wouldn't have bet on that, but it turns out it does stay nicely smooth. Okay, now here's an interesting one. It's actually the same height as the previous slide, but strategically we've made it smaller because you'll see this is now F equals 6. So this is like what you would see in an actual canal, and it's pretty unstable. You see these characteristic oscillations forming. But watch for a while. Okay, so forget about the bottom. Thanks for that, Cole. Just look at the top, and you see what's happening. It's not just, it has a linear instability forming oscillations, but then a nonlinear saturation into some kind of pattern. And as we wait longer and longer, it looks more and more like what I'm about to show you. Let's see. More and more like this. Then this is an exact solution of the Savonat equations found by Dressler in 1950 or so. That was actually issue number 1 of CPAM. It's in there. Yeah, nice. Very nice. And and here's a picture of the phenomenon. This is some kind of alpine conduit delivering water. And you see these well spaced out waves. Okay, so of course the spacing depends on how you scale your figure, but they are, what we have found is they're pretty close to, they're pretty well separated. Okay. All right, so now, why would people, well, this is an interesting phenomenon, something very nice to understand, but also in the canal delivering water, so there was a French engineer that found something like 70% loss of the water that was supposed to go through the canal, because let's go back. That's why I strategically took a small scale, because these are actually very large in the end. Remember, they reached almost the top. So they're sloshing over the side of the canal. They could perhaps also even, they're like mini rogue waves, a whole train of rogue waves. They could maybe damage your concrete, who knows? But really, they're just a lot of fun. They're really interesting. And people have studied them a lot, but not really analytically up till now.
Can I ask a stupid question?
Yeah.
So here you have Riemann data, right?
Yeah.
So how did they do it in the canal? Like the sort of setup for to see those instabilities?
Okay, this is interesting. So you can just, they form somewhat spontaneously after a while, but actually that's not so easy to see in a lab. So in a lab, often they'll put an oscillatory paddle. If you want to see them without any source forcing, you have to have a very long channel and very rough bottom. But you can see these all around you, because any kind of rough, like asphalt, is perfect. So I live in a kind of rural neighborhood. It doesn't have sidewalks. It has asphalt drain gutters, and every time it rains, you see them all over. So I used to send my kids out to take videos. Yeah. So yeah, these are not like, it's not like a shock tube. So I started out studying gas dynamical shocks, and you have to find a very special lab to see them, and then you don't actually see them. Yeah, but these you see. Okay, so that was the question. Good. All right, so here are some things that people see. Well, Okay, actually, this is a little bit in hindsight. Some, but not most roll waves are stable. Well, people weren't sure that any roll waves were stable when we began, and we weren't either. But now, this is what we know now. Okay, so for example, in '04, this is a very, this Baumforth and Mander paper is very comprehensive. In 2004, they thought these should work like Cahn-Hilliard or something, eventually all colliding, eventually coarsening to form a single wave. And yeah, there was a Pago, Pago and Schneider paper, I think it was, where they gave some evidence that multiple solitary waves might be kind of long lasting, but people just weren't sure. Solitary waves are unstable, by the way. Why? I know that easily because the end states are basically flat. That's like a constant state. And we know the constant states are unstable if F is greater than 2. But on the other hand, you need to know this other part. They don't exist unless F is bigger than 2. Like the existence problem allows them only when F is bigger than 2. So they can only be unstable. But these look almost exactly like a bunch of homoclinic waves strung together. And what they kind of stabilize each other. Very, very funny phenomenon. Okay, so yeah, so we want to, so the periodic guys are stable, individual waves are not. We want to understand that, so we have to study the stability of the periodic waves, and that means when you linearize around a periodic wave, you have a periodic coefficient operator. That brings you into the Floquet theory domain. Okay, so that adds some difficulty. Okay, so just a little bit, let's see, so what do we know? Well, I guess I've already said there's kind of conflicting results, although one thing that people really had worked out is near the onset of stability, near Froude number 2, when you have just weakly unstable waves, weakly hydrodynamically unstable fluid, then adding in viscosity, you get into the regime of Kuramoto-Sieroshinsky and other thin film approximations. And there's a very beautiful, well, a number of beautiful papers, but the most complete to me is this Bar-Nepomniachtchi in 95. And that's a very good description of what goes on there. And it turns out it's a perturbed KdV equation that governs that. Maybe not so surprising, since that's also a shallow water model. And yeah, that's successful. It's accurate for Froude number between 2 and about 2.3. That's something we really checked. So again, far from hydrodynamic engineering, hydraulic engineering problems. Okay, so another approach is another weakly nonlinear kind of expansion is a Witham type modulation equation. I'll show you one in a moment. That is approximates modulation of periodic waves by a hyperbolic system, and is often used in engineering to determine rough stability. And this, some of these have been done. There are also, that's in the smooth case with viscosity. There are some averaged equations that are hyperbolic, and it's kind of seems intuitively appealing, but it's not clear whether they're correct or not. They're not formally derived by systematically. And that was by Boudlial and Liapetevsky. So, okay, so let's see. Now, I don't want to forget, though, to say, okay, so a really important contribution was my collaborator, Pascal Noble, in 2003. In his thesis, he introduced an eigenvalue framework for this. There was none. There was no linearized theory at all. And he introduced one, and he was able to show high frequency stability for these roll waves, but not to understand the low frequencies. I mean, they're very complicated eigenvalue problems. So up to now, there was, up to when we entered, there was no real definitive result of stability for or against. Let's see if I Okay, so let's talk about, okay, viscous equations. So if you include higher order effects, you get a viscosity here. So it actually, if we keep the red term on the right and throw out the relaxation terms, now we have isentropic, viscous isentropic gas dynamic, gamma law, gamma equals 2. Okay, the solutions now are smooth, but these nice solutions of Dressler are no longer exist. That was perfect for inviscid, but and it's a very tricky problem. It's a non you sort of it serves as a non-hyperbolic rest point in the geometric singular perturbation theory. Hartrick proved convergence in the zero viscosity limit. It's not at all easy. Okay, so formal amplitude equations. Okay, here are the Bar-Nepomiansky equations. So you see the first, this is KdV, take epsilon equals 1, delta is small for us, and there's a Kuramoto-Sivashinsky type regularization. So you kind of combine both. And all right. We have shown that stability of, and these support periodic waves. Actually, they're singularly perturbed KdV conoidal waves, and that was shown by Nick Ercolani. And we've shown that stability of these periodic waves is equivalent to stability of roll waves of Saint-Venant near this onset f approaches 2. Okay. Now, a long wave approximation. So these are Witham types equations. What do they look like here? Without going through the derivation, it turns out you get a hyperbolic system in 2 variables. H bar is the average over 1 period of the height. Q bar is the average over 1 period of the flux. K, okay, so here are the waves. It's HQ of omega t plus kx. It's periodic. So this is a periodic profile, capital H, capital Q, and it depends on t and x in this way. So this is the time frequency is omega, and k is the wave number. So there is a relation between the two. It's sometimes called a nonlinear dispersion relation. Omega is a function of k. But that's determined by the existence theory. And that closes this model. Okay, so what you have in mind is that there's a slowly varying change in the phase and the wave number and high frequency oscillations. That's the derivation of this equation. So what should hyperbolicity have to do with this? Stability in this sense is just consistency of this model. Could this make sense? It can only make sense if this is well posed. That means hyperbolic. So hyperbolicity of these equations is kind of defined as some kind of rough and ready stability, like asymptotic stability. Okay, and yeah. Oh, sorry. Yes.
In the first equation, you have the amplitude equation that you obtained from your original model with or without viscosity.
That is with viscosity. You need viscosity to get this one.
In the parameter f close to 2.
Yeah. So both things. Yeah. So it's in.
Mu is anything or it's small?
Viscosity could be anything. Yeah. You could make it 1. Yeah, it's not a small viscosity. It's the small amplitude, really, or not small Froude number. Let's see. And the amplitude is the amplitude is small. The wavelength goes to infinity. It's a long wave bifurcation. It's not like a Turing bifurcation or something. It's around wave number 0. As studied by Benny and many people. Oh, whoops, wrong way. Okay, so all right. So here's the exact a sketch of the exact eigenvalue analysis of Nova, introduced by Nova. So first of all, if you want to study eigenfunctions of a periodic coefficient operator, well, If it were a constant coefficient, we would take Fourier transform and completely diagonalize it. It turns out you can diagonalize periodic coefficients by looking at functions which are periodic and satisfy, which have a twisted periodic boundary condition. So here Xi is real, so e to the I Xi x. X is we're going on 0 to x. X is the wavelength, capital X. So this is a complex modulus 1. So it's not exactly periodic, but it's moving around. We could think of Xi as very analogous to the Fourier frequency in constant coefficients. And by the way, since constant coefficient problems are periodic coefficient, trivially, this also works there. And in that case, it exactly reduces to Fourier expansion. Okay, so we're going to solve the eigenvalue equation, L minus lambda V equals 0. Here, L is the linearized operator around the wave. The wave is smooth because we're looking at the viscous one. This is the easy one. And then the periodic Evans function introduced by Rob Gardner is we are going to look for eigenvalues by looking at all solutions of the interior equation on one cell, and then we'll check whether the boundary conditions are satisfied. One way to do this is to solve things from left to right, starting with the identity, just find a fundamental solution. And then this funny bracket with the Xi is defined to be the difference between the right end state and the starting end state at 0 times this twisting. Okay, and when the determinant of that matrix is 0, then there is a linear combination of these, there is a solution for some initial data that satisfies exactly the twisted boundary conditions, and it's not identically 0. That's an eigenfunction, and so you get pairs. So pairs Xi lambda, and the lambdas are the eigenvalues. They're associated with a particular mode, which is parameterized by Xi. That's how it works. And think of Xi as like a Fourier wave number, Fourier frequency. Okay, so first results. And this comes from some earlier work of Denis Serre, is that you have first order agreement of the neutral spectra. So that is, why is there neutral spectra? Well, it turns out there are a lot of 0 eigenvalues of this linearized operator. There's one at least to do with when Xi equals 0, there's translation invariance. You can just move the wave. Xi equals 0 is when you have exactly periodic boundary conditions. There's no twisting, and that is satisfied by the wave, and the derivative of the wave satisfies the eigenvalue equation with lambda equals 0. Okay, so that's a 0 eigenvalue. It turns out there are several more due to conservation, and so there are actually 2. There are 2, and those make. It turns out that those spectral curves exactly agree with the characteristic velocities from the Witham system, from that hyperbolic system that I showed you. The physicist's version of stability, right here. You look at the characteristic velocities; they correspond to the spectral expansion of the 0 eigenmodes. Okay, well, what if this is not hyperbolic? Okay, that means it has pure imaginary, some imaginary component. I'm sorry. Some let's see. Sorry, I'm looking at the. Sorry, I want to look at the symbol of this. Where did it go? I see. I'm going the wrong button. Basically, we'll have both a real and an imaginary part if it's not hyperbolic, and that means the eigen expansion will start not with pure imaginary, but something with a real part. And that means it's going to be unstable because we can vary Xi. It's a proportional, the first order part is proportional to Xi. We can make Xi negative or positive. That means we can have a strictly positive real part eigenvalue, and it would be unstable. So this is a necessary condition for stability. Okay. And then, we also have second order agreement. And that means if you continue this expansion, this formal expansion, you need to have hyperbolic parabolicity as well. And this is something that was seen in a different way using symmetry by a beautiful paper in '86 on the Karamona-Sivashinsky equation, where they show that the periodic cells basically look like masses on springs, like a damped wave equation. They sort of bounce. That's the behavior. Nice. But really, that's what we've shown here more generally. For any periodic waves, you're going to get this hyperbolic system. And the characteristics, it's a wave equation. So it's going to be some kind of damped wave equation. Okay, so from theoretical point of view, this was a complete resolution. If you just add a little viscosity, then we can do everything. And we also found numerical, it was not easy to numerically determine these spectra, but Blake Barker did an amazing job on that. And so we could really tell what's going on. So here's Blake Barker's pictures. Okay, so what I have to tell you is, okay, you have the Froude number, but then you also have the period. And for each combination of a Froude number and a period, you get one wave. So there are a lot of these waves. Okay, so for a given Froude number, these are the upper and lower stability curves. Between them, we have stability. Outside them, they're all unstable waves. And here's a picture. So I don't know if you can see, this is a light green picture. That's the theoretical, the perturbed KdV equation, which these can be exactly determined, these boundaries. Okay, so they look, okay, interesting. They match. But then something very different happens. So in a log-log plot, we see it becomes like a straight line. So that's funny. We had thought probably there would be nothing you could say. We thought this would be it, and afterward you'd have chaos. There are some other examples where that seemed to be the case, but for Saint-Venant, no, it becomes more regular. It's just a power law. And here is a picture of the power law over here. So that's amazing, but it's amazing, but not great, because this took almost a year to produce this figure. It becomes, and as you, so it was okay in here, but we insisted on going all the way out till these things collided, and Blake Barker was really unhappy because it would take, weeks to get one more dot. And we said, oh, but maybe just one more. And in the end, we got this. So it's pretty clear what you'd like to show, but there's more. We didn't have a theoretical explanation of this. It looked like it was converging to an inviscid shape to the Dressler waves. And so, okay, so this motivated us to go back and study it from the inviscid point of view. So drop the viscosity and try to understand these large amplitude waves from the inviscid relaxation system. So, and that's our motivation. Okay, so we don't have any Witham equations. We don't know how to derive them, but we just thought, let's take the Witham equations we had before and put in a different nonlinear dispersion relation. There still is an existence theory, and we can still determine omega as a function of k. So we do that. So we have that, and then we have the competitors. This was just done by averaging, but also without derivation, so that it's a fair competition. And which one is going to give the right curves? Well, it turns out that the way to find this is actually to look at the exact periodic Evans determinant. Okay, so this is what Nobla did. So he did his in the inviscid case. All right, so now there's a jump condition, the linearized ranking Hugonio condition. So we have smooth things. We'll put the jump at the right. Okay, so we have a smooth interior equation from 0 up to x. Then we have a boundary condition at capital X at the right-hand side of the periodic cell, and we have some boundary condition. Okay, so, but we can again form, it's just whether or not there exists an eigenfunction can be expressed as a certain system of linear equations after we solve the interior equations forward, and that is a determinant condition again, and this is called it's like the Lopatinsky condition of Maida for a single shock.
Slide you had the system. That was a modification of Witham.
Yes.
Since this is the second equation of 8, just took the average value.
Yeah. So they take the average in both equations, which is yeah, why not? I mean, but it's not crazy because there is a right-hand side in the second equation, of course. but they had some justification for why that should average out to zero.
So
Yeah,
on the right-hand side, you keep two terms, the viscosity and another one.
Oh, there's no more viscosity now. Now we've thrown out viscosity because, yeah.
There's also another term that.
There was the H term and the minus U squared term. Those were both there. But since as they're in equilibrium for these solutions, one might think that they average to zero. And they do for the wave, if I recall. But I'm not going, but yeah, there's some justification. There's some intuitive reason that this might be okay, but it's not a full derivation any more than ours was. But yeah, it's going to turn out, well, I'll give it away. It's going to turn out that ours is correct, but we don't know any formal derivation. It was actually much easier to go through an exact analysis than to find a formal derivation. We couldn't come up with it. But what we did is we set up the eigenvalue problem and this determinant. And okay, so next step is an amazing thing happened. There's a very degenerate property that for lambda equals 0 and any flow k number c, this determinant vanishes. So that's really weird and unusual. That doesn't ever happen, but it does here. That means we can divide out lambda and we get lambda times delta hat, some reduced Evans-Lopatinsky determinant, and still analytic. And we can compute, its value at lambda equals 0 in closed form. Turns out it has a root of multiplicity 2. I'm going down to the corollary. At lambda equals 0, and we find two spectral curves. One is identically equal to 0, and the other is, okay, it expands like this, negative IC times something. And alpha can be calculated in closed form. Well, why is this useful? Well, this tells us a lot of things. This one is not very interesting. This is the one that's going to determine stability. And first order in C is just alpha IC, it's neutral. That's good, so it's not unstable, but it's never unstable. It's not going to tell us any stability information. So unfortunately, even if our Witham type model is right, it's not giving information enough to determine stability. We're actually finding it here. The interesting thing though is that alpha, not only, which is the basic idea is usually you can calculate the first order perturbation, but not the second. The second you do somehow by spectral theory or usually numerically. But in this special case, they both have the same coefficient alpha because gamma turns out to be something that it never changes sign. So the sign of alpha determines both the sign of the first order and the sign of the second order. It determines stability. And so therefore we can this quantity sine of alpha, it gives us a low frequency stability condition. It's basically determined as you solve a cubic equation in F, and you can find that lower boundary that took almost a year to compute in the viscous case. Okay, so here's the end result. So the straight averaging, the BL model didn't capture low frequency stability. It gave false positives and negatives. It just didn't work. Ours worked, but it's useless. It doesn't. It always says stability. The worst thing that happens is you get a Jordan block at alpha at the stability boundary. It's signaled kind of by a Jordan block. Something funny happens, but you don't really notice it. You really need to have the full analysis. Turns out, to get what I would call kind of an engineering type answer, those are usually gotten by formal asymptotics. Here it was better to do the full theory. And here's the picture that we get. And this still took a while, but it's like 50 hours, so a week or so. These are these are real hours on the, Okay, so here's just a picture of the existence region is the colored region. The red is the stable ones. And down below, well, there's a very thin region here that you can't even see. The inviscid one is collapsed at the bottom. Okay, so the upper, why did this take 50 hours? Not to solve a cubic in F. That was the lower boundary. The upper boundary we had to find numerically. And all I can say about that is very close to the lower boundary. So maybe it doesn't matter so much. So you know what the waves look like pretty well. Okay. This is just a picture of different, the spectra that you get. It just to show that it can be very interesting. A lot of geometric bifurcations and things of the spectra. All this spectra, by the way, is continuous spectra. So it's a period, that's as is typical for periodic coefficient. So a lot of room for behavior. Here's a comparison with the viscous case. The black dots are the viscous, and the red is the lower stability boundary that's calculated explicitly from a cubic. It just agrees very well with the viscous one. The upper boundary, well, it looks like the viscous is collapsing. We could think of maybe zero viscosity involves collapsing of this upper curve, upper boundary. We don't really know. At the onset, so near F equals 2, that's interesting. There is a sort of different behavior at onset. But it's not the viscous one. It's not the one of Barr and Nepomniachtchi, and it's not the perturbed KdV. Something else for inviscid. Maybe that's interesting. I don't know. I kind of feel like the most interesting cases are the viscous case near onset, which has to do with a variety of thin film behavior, and then this Saint-Venant far away from onset, the large amplitude case. So I think this comparison I haven't gone further with, but that would be interesting to determine at a mathematical level, I think. All right. And so the takeaway, this explains the power law that we saw before. It is a power law, a solution of a cubic, and disregarding lower order terms. So it's converging to some power law. There is this inviscid transformation at onset, but it's different in nature from the viscous one. Okay, it would be interesting to formally derive this inviscid amplitude equation in some sensible way, other than guessing. But on the other hand, it still doesn't tell you the stability. For that, you need the theoretical framework that Nobla gave. And that's so very important. There is a strong analogy to detonation, and in all this, because detonation also is a conservation law on one side, and it has some forcing on the other side. There was kind of again, you can exactly solve the inviscid problem, but you can't prove nonlinear stability there, or no one has yet. So what you sort of do is use a nonlinear stability result for the viscous case, and you figure out the spectra from the inviscid limit. So you could do that here, but actually we're going farther. And a lot of this, we've now proved nonlinear stability for these waves. In particular, the shock waves that I showed you pictures of at the beginning. Those have been proved completely analytically, no numerics. They're proved to be always stable in 1D. Okay, so that is the ones that were stable. That is F less than 2. Okay, so many interesting directions. Oh, I forgot the most important one. Okay, all this framework, it's not specific to Saint-Venant. It works for general equations, in particular for larger systems. And there is a larger system that we would very much like to study, recently introduced, not so recent now, but last 10 years also. Richard and Gavriluc introduced a model that incorporates vorticity effects inside the fluid, which were previously absent. And something very interesting happens, which is, all right, now I'm going to talk about the experiments of Brock. He had a wire above the waves and with a sensor on the height of the waves, and he got amazingly very good pictures of the shape of the waves. And the shape of the waves is the black dots. The Dressler exact solutions of Saint-Venant are the blue curves. And you see there's an overshoot problem here. Okay, but Richard Gavrilut, which we could think of as it turns out to be compressible Euler with the energy equation, some energy equation, and then a right-hand side. So that's kind of fun. And that's incorporating another entropy. And look how it matches with the experiment. You can't see any daylight there. Brock also did this, but by matched asymptotics kind of, this is from first principles. This is just from the equations. Brock kind of matched up things and fixed this in a nice way. And let's see, did I have, oh, I'll show you in the next talk a picture of Brock's apparatus. Okay, let's stop here and have a break.